that we had face-to-face in class on October 25th. I'm just going to go forward a bit with the next phase of talking about the cepstrum, and that is the male frequency cepstral coefficients. We may have begun this subject matter a little bit in the previous lecture. I honestly don't remember where exactly we stopped, but I believe it was about here. So if you recall these slides and want to skip forward, that's fine. But what I want to do is discuss using the cepstral coefficients, because it's the cepstral coefficients that are largely used as a feature set for the human voice for various operations. I've taken most of these lecture notes from the following online book. There is a modern version of the online book and then an older version, and I actually kind of prefer the older version, so that's what I'm using in the course of this lecture. So we need to go back to the description of the mel frequency. Remember that's short for melodic. And remember, the mel frequency scale is a scale that kind of follows the filtering bandwidths of the human ear. So calculating the mel frequency cepstral coefficients is similar to how the human ear would work in the audio processing. And so these features, there's usually about 10 or 20. They're going to describe the overall shape of the spectral envelope. They were, prior to deep learning and the advent of deep learning and AI, the mel frequency cepstral coefficients were probably the number one technique used for voice recognition. They're used as a description for this term called timbre, which is this sometimes qualitative term that's used to describe how audio signals sound. In the next few slides, I'll go over how the cepstrum is used to illustrate the identification of the fundamental frequency. So, power spectrum of windows of speech signals contain information about the most important features of speech signals, like the identity of vowels. But unfortunately, the range of values is very non-uniform, and if you look directly at the power spectrum, you really don't see anything that's informative. The logarithmic spectrum is, as you know, a much more acceptable representation. It's more visual. It approximates the sensitivity of the ear. And so the logarithmic spectrum can be used to assess the auditory importance of spectral features. The logarithmic spectrum visualizes spectral content such that the magnitude of the values is approximately uniform throughout the spectrum. The only exception are zeros and other very small values in the magnitude spectrum, which will give negative infinity or very large values in the log spectrum. And so those are difficult for visualizations, but they're not of great consequence for auditory perception, but can be ignored. Now, for computations in the log spectrum, arbitrarily large negative values are a problem. So to reduce the likelihood of those kinds of problematic values, people use an energy bias similar to what's referred to as a mu-law rule. In other words, they will integrate energies over frequencies. So in other words, specifically, instead of y is equal to the log of x squared, we use y is equal to the log of x squared plus e, where e is some small positive number. And so that way you avoid the issue of when x approaches 0 of getting an infinite, or when x approaches dc of getting an infinite output. So you can look then and see as just an expression of integrating over neighboring frequencies where y is a scalar. The likelihood that all three of these are all simultaneously near 0 is much less than one being near 0. So in other words, by sort of doing a smoothing operation, you avoid some of the problems. So estimating the fundamental frequency in the cepstrum. So the statement is in fact very simple and relatively robust. I've done this before, and I would not say it is very simple, but it's doable. And there are some existing codes that will do this for you, including in MATLAB. MathWorks has both in Simulink and MATLAB the ability to find the Kepstrel estimate and the fundamental frequency estimation. So fundamental frequency estimation going to be discussed further in a separate section. But what we have here is actually this was implemented with Python code, and if you look up this in this reference, you'll find they do give the Python code. I have not shown it here, but and once again, I'm pretty sure we got this far in the last lecture. But we have a windowed speech signal. We then have the power spectrum, the log spectrum, and then you can clearly see here's our fundamental frequency showing up in the Kepstrom. Now the Kepstrel coefficients, as we talked about early in the lecture, was you basically take this MEL frequency scale and you implement like a filter bank based on the MEL frequency scale. So let me show you. So this is the equation that relates the frequency to MEL transform, and we can find the inverse transform by basically just inverting the equation. So taking the exponential of what's inside the brackets here. So by taking equally spaced points using the previous formula, so equally spaced points in the MEL scale, you can find the frequency points whose perceptual distance is equal. In other words, to sample the log spectrum with a perceptual scale, you would pick samples at frequencies fk. So you start off with your MEL frequency, and you sample in the MEL frequency at equal intervals. So that's what your M sub k is. Those equal intervals do not correspond to equal intervals on the frequency scale. So you want to avoid that the distance between subsequent f sub k's gets smaller than the highest distance between harmonic peaks, so that the model focuses on the macroscopic structure and ignores the fundamental frequency. So usually you have a minimum threshold that's applied to your kth frequency sample. If you pick only samples at f sub k, you lose all the other information. So similar to that frequency integration approach, you take a weighted sum of energies near the target frequency, and thus you get this u of k, where the w of k and h are these weighting parameters. And so then what you get is you get the benefit of a robust estimate due to energy integration, but you've also applied the perceptual frequency scale. And then what's commonly done is you take the discrete cosine transform. Now this is different from the discrete Fourier transform, and MATLAB has absolutely an algorithm that will do this for you. So what MATLAB will do is it will basically take the MEL frequency scale, and it will take, rather than using the Fourier transform, it takes the discrete cosine transform of the parameters, and then basically the goal here is to be able to decorrelate the signal. So these weighting coefficients are usually chosen as triangular functions. So that would mean it's like you're applying a triangular filter bank. So the process of getting the MFCCs from a spectrogram is going to be shown, I believe, on the next slide, where you apply a triangular filter bank placed at linear steps on the MEL frequency scale, which will be non-linear steps on the frequency scale. And so then we're going to show, I believe in the next slide, we'll see a figure of the triangular filter bank and the spectrogram of a segment of speech. When each window of the spectrogram is multiplied with the triangular filter bank, you can see the MEL weighted spectrum that should be illustrated in the third figure. So let's The fourth figure then is going to show the outcome once that spectrogram is multiplied with a discrete cosine transform to obtain these final Kepstrel coefficients. So here's our triangular filter bank. So this is the set of filters that we're going to apply to our signal. And so once that's applied, you can see we have a spectrogram of a segment of speech in the lower left, and then we have a male-weighted filter bank in the upper right. You then calculate the male frequency Kepstrel coefficients, and you get a figure that looks roughly like this, where we're plotting index versus time. So the MFCCs have become one of the most widely used features in speech and audio applications, mostly because it works, and compared to other techniques, it is relatively straightforward to implement. So if you're unsure what inputs to give a speech and audio recognition, the first thing to try are the MFCCs. The advantages, it quantifies the gross shape of the spectrum, which is important, for example, in identification of vowels. At the same time, it removes the fine spectral structure, so this microlevel structure, which is often less important, and it thus focuses on that part of the signal which is most informative. Secondly, straightforward and computationally reasonable, efficient calculation. So I did reply to an email question that I received that, you read a lot about how simple this is. My own personal experience is I tried to do this a few times, and it's okay. It's just not as simple as I didn't think it was as simple as they say. And then finally, the performance of these coefficients is well tested and well understood. Some of the issues. So the choice of the perceptual scale is not particularly well motivated. Other scales like gamma tone, filter banks, and others might be better suited, but because they haven't been investigated as widely, the male scale has just persisted. The coefficients are not robust to noise, so the performance of the MFCCs in the presence of additive noise has not always been good, and that is a significant problem. The choice of the triangular weighting filters is arbitrary and not based on well-grounded motivations. Alternatives have been presented, but they haven't gained popularity, probably due to having a relatively minor effect on the outcome. And then finally, they work well in analysis, but for synthesis, they're problematic. Namely, because it is difficult to find an inverse transform from MFCCs to power spectra that is both unbiased and congruent with its physical representation. In other words, the power spectrum must be positive. Now, a lot of this has to do with the signal processing consequences of as soon as you begin to work with the power spectrum, you've lost phase information. And so when you've lost phase information, and then you take the cosine transform as well and the logarithmic transform, reversing that process to get the original signal back is actually very difficult, and you have to do some weird things like take a Hilbert transform so that you add the imaginary components back, and it gets a lot more complicated. So when you have recognition tasks like phoneme recognition or voice activity detection, one of the classic input features are the MFCCs. And they describe the instantaneous spectral envelope shape of the speech signal. But speech signals are time variant, and they are constantly changing. So though we describe speech in linguistics as concatenated sequences of phonemes, the acoustic signal is actually much more accurately described as a sequence of transitions between phonemes. And the same observation applies to other features of speech, like the fundamental frequency, and that describes an instantaneous value. A lot of times it's more informative to analyze the overall shape of the fundamental frequency track than the absolute value, For example, emphasis in a sentence is also often encoded with a distinct high to low contrast in F sub 0, and questions in many languages characteristic low high fundamental frequency contour. Okay, what does this statement mean? So what this statement means is it means that as you speak, the fundamental frequency of your voice shifts around, it moves, it's constantly changing. When you ask a question, there is a low to high transition. A lot of times when people are confused, you will hear their voices drop and slow, and so that's another transition of fundamental frequency. And then the fundamental frequency shifts when people want to place emphasis. Some of it is volume, but some of it is also fundamental frequency. So one of the things that we really struggled with when we were trying to figure out if you want to, for cocktail party effects, if you want to track the fundamental frequency of an individual speaker, then you do have to take into account that there are these patterns of transition from low to high and high to low. And if you have multiple speakers in an environment, sometimes those patterns of transition will cross. So if you're picking out multiple fundamental frequencies and trying to track them, it's hard to know whether you're skipping from one speaker to another when the fundamental frequencies get close in the frequency domain. So that's a problem with fundamental frequency and trying to track fundamental frequency. What we did when we were trying to do this is we trained a neural network with voice inflections, just common standard voice inflections. And so for our input in our training set, we had low to high, high to low, low, high, low, high, and so on. Just common conversational fundamental frequency shifts. And so we trained the neural network to recognize those patterns. And then we used the neural network to make a prediction of where the fundamental frequency would go next. So it was a time predictive neural network that was taking all of the past variables and then making a prediction based on the training set where what the path would be for future values in time. So in this book, they talk about a common method for extracting information about transitions is to determine the first difference of signal features, which is known as the delta of a feature. So you have some feature f sub k taken at time instant k. The delta is basically the difference, okay, between k and k plus 1. The second difference is called the delta, and it's basically the difference of the difference. So features in a recognition system are appended by their delta and delta features. That gives you triple the number of features without much computational overhead. So you would take your normal fundamental frequency-based features, your f sub k's, and then you would take the difference, and then you would take the difference of the difference, and that would give you 3 sets of features on which to train. So basically, if you just kind of think of this, the delta represents roughly the first derivative, and the delta represents the second derivative of the signal. As estimates of the derivatives, they're not particularly accurate, but they're very simple, and so they're a very simple thing to do. So it's a simple calculation, not very computationally costly. The issue with accuracy is that differentiators obviously tend to amplify white noise, where the desired signal remains unchanged. So consequently, the output will be more noisy than the original signal, and the fact that differentiation is applied twice means that this is kind of an accumulated problem. So these are linear transformations of input features, and if they're combined with a linear layer in a neural network, then the 2 consecutive linear layers are redundant, but they can still provide a convergence kind of benefit. So the delta feature and delta feature are classic components of machine learning algorithms, and they're successful because they're very simple and often provide a benefit over just the instantaneous features. So here's the equations for the delta and the delta delta. Okay, so now let's talk a bit about the MATLAB algorithms that calculate the MFCCs. So basically, MATLAB has built into its signal processing toolbox the MFCC, which is going to do this operation for you. And so this is the command and the appropriate syntax. Audio in is basically the audio file. And if you just do this without any additional specifications, what you will get as an output is the Mel frequency Kepstrel coefficients for the audio input, sampled at a frequency of f of s hertz. So you will have to give it the audio signal and f of s. If you don't have any other output arguments, it will plot the Mel frequency Kepstrel coefficients. Before plotting, it does normalize the coefficients to have a mean of 0 and a standard deviation of 1. If the input's in the time domain, then the Kepstrel coefficients will be plotted versus time. If it's in the frequency domain, they're plotted versus frame number. And if the log energy is extracted, then it is also plotted. You do have the ability to give it some output. Let's see, where is that? Right here, second line. You do have the ability to give it some, put the output in an array. And so using this syntax underlined in blue here, you can get the coefficients. You can get delta, you can get delta delta, and you can get something called LOC, which is the location of the last sample in each input frame. So then you can just use the MFCC command alone to get the plot. So here's a plot. Here's time. Here are the Kepstrel coefficients. You can see that they do change. This is log of the energy, and this is the time in seconds. So in this plot, we're getting the Kepstrel coefficient as a function of time, and notice that we're getting 12 of those. And by the way, in this previous example where it is giving you an output of, where did that go? Sorry. It's giving you an output of the coefficients delta and delta delta. Then those are useful if you do want to use those as input to a machine learning system. You get those out of this calculation. So one possible project for those of you who are still looking into a project is to look and see using just a standard MATLAB implementation of a simple neural network, using that in combination with this feature set to identify different vowels, possibly the ones we took in the class where we made the recordings, taking a different sound and seeing the effectiveness of using the Kepstrel coefficients alone, using the Kepstrel coefficients with the other two inputs. That would be a possible project if you're interested in doing that. You can extract the Kepstrel coefficients from frequency domain audio as well. So here's a windowed audio signal where you've taken the Fourier transform, and then you can get the coefficients with the frequency domain audio, and they've done that here. A lot of times the observations are converted to summary statistics, to using classification tasks, so you can plot a probability density function for one of the coefficients to observe its distribution. So what would that mean? That would mean you're looking at a distribution function of one of the bands that the Kepstrel coefficient draws from. So you would be picking that particular frequency band according to the male frequency, the triangular filter that was applied. You'd be taking that and you'd be looking to see how that coefficient varies statistically. So here's a histogram. When speaking of that, this is coefficient 4, and this is just a histogram. Remember, these are normalized to have a mean of 0 and a standard deviation of 1. So when you take coefficient 4, you can see that for this particular sample of speech, it's the middle here of the distribution function kind of ranges from 0.2 to 0.4-ish. It looks sort of Gaussian. You've got a little bit of spread here on the tails, but that's sort of a histogram using some summary statistics on the Kestrel coefficients. Okay, at this point I want to stop this particular video and we'll post this one, and then the next one we'll take a completely different turn and we'll look at linear predictive coding.